Welcome back to D215. My name is Alex Harris, but if you were one of my former students, I'm sure you knew me as Mr. Harris, and in today's video, we'll be discussing. In high school physics, you likely learned that a vector quantity is any value defined by both its magnitude and direction, whereas a scalar quantity is only ever concerned with magnitude. Now, to understand what I really mean here, when I say magnitude, I mean how large it is. The direction gives us a sense of the vector, like which way it's pointing. Now, when we're trying to symbolically represent a vector versus a scalar quantity, we typically or traditionally put a vector hat above the variable for that vectored quantity. Whereas a scalar, given that it's been the values we've dealt with throughout all of high school, doesn't get the vector hat. Now, there's an interesting implication here, right? When you were dealing with scalar quantities, you knew that there were negative values. And if I said I had a scalar quantity with -5 versus +5, I knew that the -5 value was smaller. It was to the left on the number line. With a vector, I can't make the same claim. The positive and negatives when they come to vectors really give us a sense of direction, pointing in the positive x, pointing in the negative x. Right? So if I have two vectors that have the same magnitude, let's just say for argument's sake 5 meters per second, but one of them is in the positive direction and one's the negative, I might shorthand that to +5 meters per second versus -5 meters per second. Now, that -5 meters per second is not smaller than the +5 meters per second in the same way it would have been for a scalar quantity. So just make sure you're mindful of when you're dealing with vectors and what that positive and negative mean. They simply mean direction, in which way it is pointing. To represent our vectors, we're going to begin with a Cartesian coordinate system indicating our positive x and positive y direction. On the diagram, I've already included the vector, represented here graphically with an arrow, symbolically here with an f, vector hat included, and down here with its values. We're going to say that vector f is 10 newtons at 53.13 degrees. In math or physics, we typically associate the x as 0 degrees, positive x, the positive y as 90 degrees, the negative x as 180 degrees, and the negative y as 270 degrees. We know that this vector must be in the first quadrant because it's less than 90 degrees. Now, one of the most common things we need to do when working with vectors is to break it down into its components. That is, how much of this vector exists in the x and y dimension. You'll actually hear this referred to as rectangular components all the time in university, and it's to differentiate from the different ways we can represent vectors. Now, when I want to draw this out using our rectangular component method, it's easy to picture it if you draw it out. So I'm going to do just that. With the blue marker, I've indicated how far this vector goes in the x direction. We can do the same with the y. I'll use a different color by going perpendicular to the x-axis. And what I've done now is represented, here's the x component of vector f, here's the y component of vector f. If I ever want to know what the magnitudes of these two components are, I do have to do a little bit of math. Luckily, it's a triangle, and the math isn't terribly challenging. I can determine vector f in the x by saying, well, it's got to be equal to the magnitude of vector f, magnitude of vector f represented here with absolute bars to tell me I don't care about the direction of vector f, only how large it is, multiplied by cosine theta. Cosine theta. So when I want to do this operation, I can plug in 10 newtons multiplied by cosine 53.13 degrees, and I will get 6 newtons. I can repeat this process for the y dimension, accepting that we're going to get a different value because we're not going to use cosine. The y component's not adjacent to the angle, it's opposite, that uses sine. So the y component equals the magnitude of f multiplied by sine theta to equal 8 newtons. And what we've just done is determine the rectangular components of vector f. It is important to note that because this is in the first quadrant, both of my components would be positive. Now, when it comes to vector notation, there's actually a couple systems we can use. The one we've already done, rectangular components, typically are associated with high school, and they're very useful for two-dimensional problems. However, it can be quite cumbersome if you're evaluating a vector in 3 dimensions. In fact, I would argue this is probably more complex than this notation down here that I'm going to introduce you to. The notation we often use with 3-dimensional vectors in university is called the unit vector notation. A unit vector is simply saying that there's one unit in every given dimension, one in the x, one in the y, one in the z. And we can represent those with I, j, and k hat. So anything in the x direction would have I hat associated with it, something in the y would be j hat, and something in the z would be k hat. What each of these are basically saying is that, hey, that's one I, that must be one unit in the x direction. One j, one unit in the y direction. If we were to try to represent this vector using unit vector notation, well, we could just write down f vector must equal 6i, since it's going 6 units in the positive I direction, plus 8j hat, because it's going 8 units in the positive y direction. Now, this vector does have units associated with it, newtons, so we are going to put brackets around the unit vector notation and put newtons right there. This is one of the more useful ways to do operations mathematically with vectors in more than 2 directions, but we can represent a 2-dimensional vector this way as well. You're going to see this a lot when we are doing electromagnetism, but this will also come up when we do the cross product in this mini-series. The last thing I want to leave you today is understanding which way the positive z direction is pointing. To do so, we're going to have to use something called the right-hand rule. Now, just to begin, the x still going to the right, the y still going up to represent our 2 positive directions. The right-hand rule uses your right hand, it has to be your right hand. You take your index finger, you point it in the positive x direction. You take your middle finger and you point it in the positive y dimension, like this, right? Positive x, positive y. Then naturally let your thumb point out. Point out. That'll indicate to you where the positive z direction is. So with this coordinate system, we know the positive x is to the right, the positive y is up, and the positive z is coming towards you. The right-hand rule. This will come up a lot in electromagnetism, but also in our vector section when we talk about the cross product. So make sure you're comfortable right hand to determine our dimensions. I want to thank you today for joining us and D215 Physics for our first lesson on vectors. If you ever have any questions or comments, please feel free to reach out, and I hope you have a wonderful day.